Hello dear classmates, welcome back to the defect-based testing. Today we are going to talk about a very important DBT technique, IDDQ testing, which was proposed very early. So what is IDDQ testing? In IDDQ testing, we measure static power supply current with certain test patterns applied. The name IDDQ represents power supply current from VDD. The letter Q represents quiescent, which means we apply a certain test pattern and we wait for a certain amount of time so that the circuit becomes stable. IDDQ testing was widely used, but it was first officially presented by Levy in ITC 81. It is probably the most commonly used DBT in CMOS technology. The motivations to use IDDQ can be first, we want to improve our DPM. In early 1990s, the target DPM was 3 DPM. It is a very ambitious goal. To achieve this goal, Boolean testing alone is not good enough. We must rely on the other kinds of testing, such as IDDQ. And the second motivation is to improve the reliability of our chip, because chip passing Boolean tests may fail early in their lifetime. So IDDQ is probably the most popular DBT that are still in use even today. The idea of IDDQ testing is actually very simple. For a good CMOS circuit, ideally, the IDDQ should be very low, as is shown in this figure. When we apply a test pattern, there could be some transient current, but if we wait for a while, the IDDQ current should be very low. However, for a defective CMOS circuit, for example, suppose we have a gate oxide short between the gate and the drain in this circuit. In this case, we can observe a static current even we wait for a long time. So we can tell the difference between good circuit and a defective circuit. Sometimes IDDQ can detect defects that are missed by Boolean testing. For example, suppose we have a high impedance bridging defect between these two wires. When we apply a test pattern, a 0 volt and a 5 volt to these two inverters, due to the defect, the voltage here can be 3.5 volt and 0.8 volt. After two inverters, the output voltage can be observed as logic 0 and the logic 1 respectively. So we cannot detect the defect using Boolean test. However, we can observe a static high IDDQ current. So this circuit may pass Boolean testing, but it may fail IDDQ testing. But now, here is a good question, FFT for you. Since this circuit already passed Boolean testing, why do we bother to detect this defect? Please think about it. There are many other defects that can be detected by IDDQ testing. For example, signal to signal bridging, signal to power, or ground to power short, or gate oxide short. We can also detect VT shift, which can cause increased leakage current, and many other defects. On the other hand, open defects may or may not be detected by IDDQ testing. For example, suppose we have open defect here. So this pair of NMOS and PMOS transistor are open at the same time. So whether it will cause IDDQ depends on the 14 gate voltage. Similar thing happen to an open NMOS gate or PMOS open transistor gate. According to Stanford's experiment, there were 5,500 chips tested and 116 of them are defective, out of which 7 chips were diagnosed to have opens. Among these 7 chips, 4 of them had high IDDQ, but the other 3 had low IDDQ. So we may or may not detect open defect using IDDQ. Also, IDDQ is not perfect. There are some defects that cannot be detected by IDDQ. For example, suppose we have a high impedance resisted open defect here. Since this defect is on the signal path, so we cannot observe high IDDQ. Also, suppose we have a feedback bridging defect here. Because this is an even parity, so this will not cause high IDDQ. So in conclusion, IDDQ is a very good DBT, but it cannot detect all defects. So now, let's look at the full model and test pattern generation for IDDQ. There are many different types of defects that can be detected by IDDQ. So, there is actually no universally good full model for all kinds of defects. There are some popular full models, for example, transistor stuck-on fault. Suppose this PMOS is stuck on. To detect this fault, we can apply logic 1. For this NMOS stuck-on fault, we can apply 0. We also have other popular fault models such as pseudo stuck-at, bridging fault, leakage fault, etc. So, how do we generate test patterns for IDDQ? IDDQ test pattern can be either generated by ADBG or selected from existing patterns. A very important idea is that the test length of IDDQ pattern must be very short because IDE testing is very slow. If we want to minimize test costs, we want to minimize number of test patterns. Most commercial ADBG tools support this test set, toggle test set or pseudo stuck-at test set. For example, suppose this NAND gate is our gate under test. We can apply 0011 to have 100% toggle coverage for this NAND gate. The pseudo stuck-at test set is very similar to a traditional single stuck-at fault test set. However, to minimize our test time, this test set only activates single stuck-at fault, but the fault effect need not to be propagated to primary output or pseudo primary output. We don't need this propagation because IDDQ can be directly measured by current. For example, suppose this NAND gate is our gate under test. When we apply 01, we can activate A stuck-at 14 and the C stuck-at 04. When we apply 10, we can activate this 24. When we apply 11, we can activate 34. So, we only need 3 test patterns to have 100% pseudo stuck-at test set. And we don't need to worry about fault effect propagation. So you must remember that IDDQ test set must be very short to be applied at minimum cost. Now it's time for you to work on the quiz. Given this circuit, please select 3 best toggle test patterns for the IDDQ. Now please pause the video and work on this quiz. Okay, are you finished? Since we want to have good toggle coverage, so we can observe that for signal B, we have only one here. For signal J, we have only one. In the K, we have only one here. So we select P1 and the P2 and the P4. If we select these three patterns, then we can have 100% toggle coverage. So the answer is P1, P2, and the P4. So, have you got it correctly? Okay, now let's look at some practical issues of IDDQ testing. So, how do we measure IDDQ testing? There are three ways to perform IDDQ testing. The first one is that we can directly measure IDDQ from the tester, ATE. The second method is that we can implement some current supply monitor on the test board. Or the third method, we can implement an on-chip built-in current sensor, BICS, on the chip. So, for the first method, ATE measurement, we can use a precise measurement unit or PMU to measure IDDQ current directly. The procedure is like this. First, we apply a test pattern and we pause at pre-selected pattern and we wait for about 1 to 10 milliseconds until the CUT internal node to become stable, and we use ATE to measure the power supply current. The CUT failed the test if it is larger than the user-defined threshold. We continue this loop until we measured IDDQ for all the selected patterns. The advantage of this method is that we don't need extra equipment and we don't need to change the circuit design. However, ATE measurement suffers from long test time. Also, the background leakage current is large. If we use a built-in current sensor, we can have a self-test capability. As is shown in this figure, we can implement a current mirror to measure the IDDQ current. So I0 is approximately the same as IDD, and we can have an on-chip current measurement circuit. If the current is low, it passes the test. The advantage of this built-in current sensor is that we can have built-in self-test of the chip, and we can also partition the CUT so that the background leakage current can be reduced. However, this built-in current sensor can result in performance degradation because the power supply here is not the real power supply. So there can be voltage drop between these two power supplies. Also, we suffer from area overhead. So now let's look at some real experimental data of IDDQ testing. This is a HP experiment. They test 26,000 CMOS static logic circuit, and the current distribution is like this. We can see a threshold around 30 microamp. If the IDDQ is larger than 30 microamp, it failed the test. This Venn diagram shows the experimental result. The red circle shows the number of chips that fail functional verification testing. The yellow circle shows the number of chips that fail scan test, and the blue circle shows the number of chips that fail IDDQ test. We can see that there are about 4,000 chips that failed IDDQ testing, out of which 1.3 thousand chips fail only IDDQ and they pass functional test and the scan test. So we can see that there are some defects that are only detected by IDDQ. They cannot be detected by other test methods. This is another experiment performed by IBM. They measure IDDQ and then they perform burn-in. This picture shows the failure rate after the burn-in. The x-axis shows the IDDQ current. We can see that the failure rate after burn-in is low for low IDDQ chip, but it increases with high IDDQ. That means that if the IDDQ current is higher, it's more likely to be an unreliable chip. So, what are the issues and the solutions for IDDQ testing? This slide shows the problems of IDDQ testing. First of all, this is a very slow test. It takes several milliseconds per measurement if we want to measure IDDQ on a ATE. So it's a very costly test. Second, IDDQ testing is a trade-off between yield loss and the reliability. We see IDDQ only failure chip in the previous experiment, and we don't know which of the chips that fail IDDQ is really defective. And the third issue is that IDDQ testing is not applicable to all designs. For example, analog, mixed signal, and memory circuits, they are not suitable for IDDQ testing. Finally, IDDQ testing is losing effectiveness in advanced technologies. This is due to increasing background leakage current, and it's hard to set a single threshold to distinguish good chip and defective chips. This slide shows many different leakage current. There can be categorized into three categories: the substrate leakage from drain to source, and junction leakage from drain to substrate. Also gate leakage from gate to the channel. This is a traditional planar CMOS technology. So at the end of 1990s, it was predicted that IDDQ testing cannot scale with technology. As shown in this picture, suppose this is a distribution of good chip, and this is the IDDQ distribution of defective chip. The mean of these two populations are getting closer and closer. So it was predicted that in the year 2000, we will not be able to use IDDQ anymore. So what are the good solutions for IDDQ testing? Turns out the most effective way to reduce background leakage is the FinFET technology proposed by Professor Hu of UC Berkeley. FinFET can greatly reduce background leakage so that IDDQ can still be used. The second one is that we can bias the substrate. This will provide dramatic improvement of leakage current. However, this will require some design change, so it's not very popular. Also, we can use lower temperature. If we reduce the temperature, we can reduce IDDQ significantly. However, this could be very expensive for testing. We can also use multiple VT technology. For example, we can use some high VT low leakage logic gate on the non-critical path. Finally, we can use circuit partition, so we can use built-in current sensor to measure some certain block of the chip. If we don't want to change the design or technology, there are some data processing techniques available. We don't want to set a single threshold, so we collect all the IDDQ data and then we do post-data processing to make a pass-fail decision. Here we list 3 techniques. The first one is delta IDDQ. We take the difference of maximum IDDQ and the minimum IDDQ, and we fail the chip if delta IDDQ is larger than a certain limit. As shown in this figure, suppose this chip has IDDQ distribution like this. On the right, this chip has IDDQ distribution like this. The left hand side, the delta IDDQ is small. On the right hand side, the delta IDDQ is very large. So this chip may fail the test, but this one can pass the test. Also, we can use some idea like current ratio. In this technique, we plot the maximum IDDQ versus minimum IDDQ, and we calculate the slope of this curve. In this way, we can identify outliers. If this chip has a different slope than a population, then we suspect they are defective chip, so they fail the test. Also, we can perform spatial analysis. The idea is that IDDQ is highly correlated to the neighborhood. Professor Dash proposed nearest neighbor residue method. In this method, we record all the IDDQ data on the whole wafer, and we can estimate a die's IDDQ. If the IDDQ of a die is very different from our expectation, then it failed the test. For example, on this wafer map, a white color indicates very low IDDQ and dark color indicate high IDDQ. In this neighborhood, we see very low IDDQ, but this particular die has an exceptionally high IDDQ. So this may be a bad die. On the other hand, in this neighborhood, the IDDQ are typically very high. So these dies may be good dies. So we can make a pass-fail decision using the wafer map. Now it's time for you to work on the quiz. Which of the following is not correct for IDDQ? A. IDDQ can still be used with careful data analysis. B. IDDQ is lower at lower temperature. C. Chips fail IDDQ are all defective chips. Please now think about these questions. Okay. The A is correct. B is also correct. C is not correct. There are chips that pass IDDQ which are still functionally correct. Have you got it correctly? Okay, in summary, for IDDQ testing, it's a very effective way to improve reliability and DPM. However, we can see trade-off of test quality and reliability. For IDDQ testing, we can apply different test patterns, such as toggle test or pseudo-socket test, but the test length must be very short. And we have different solutions to process the data to enhance the effectiveness of IDDQ. real experimental data show that higher IDDQ are likely to fail after burning. From this Venn diagram, we can see that functional verification test, scan test, and IDDQ testing, they all have unique failures. So each test detects unique defect, so no test can replace any other test. Finally, is a FFT for you. Since this chip already passed our logic test, why do we need to worry about this defect? Okay, thank you for watching.